Ever wondered if light can actually push objects? Radiation pressure, also known as light pressure, happens when light, or electromagnetic radiation, transfers momentum to matter. Basically, when light hits a surface, it gives that surface a tiny push. Imagine light as tiny particles called photons. Each photon carries a bit of momentum described by the equation P equals h over lambda, where P is momentum, h is Planck's constant, and lambda is the wavelength of light. When light perfectly reflects off a surface, the momentum change of the photons has to be balanced by the same change in momentum of the surface, thanks to Newton's third law. Radiation pressure can occur through different processes. When light is soaked up by an object, it gives the object a nudge. Perfectly reflected light transfers momentum to the surface it bounces off. When matter emits light, like in blackbody radiation, it also feels radiation pressure. Now, why does this matter? In space, radiation pressure plays a big role. It helps steer spacecraft, and ignoring it could throw off their courses. In astrophysics, radiation pressure from starlight is crucial in stellar processes, sometimes even overpowering gas pressure. Laser technology harnesses radiation pressure in amazing ways, like laser cooling, optical tweezers, and even beam-powered propulsion. These innovations have even snagged Nobel Prizes. What if we could use light to push a spacecraft? In 2015, scientists saw evidence of light pushing, not just pulling. Picture intense laser beams driving a spacecraft by pushing on its sail. Could this be the future of space travel? Before we delve deeper into the mysteries of light and its properties, let's take a moment to understand what actually is light. Light is electromagnetic radiation that can be detected by the human eye. It spans a visible spectrum of wavelengths from about 400 nanometers, nm, for violet light to approximately 700 nanometers for red light. Beyond this narrow band, there are regions such as infrared with longer wavelengths and ultraviolet with shorter wavelengths. The speed of light in a vacuum is a fundamental constant, approximately 299,792,458 meters per second, or about 186,282 miles per second. This incredible speed means that light can travel around the Earth 7.5 times in just 1 second. Light serves various purposes in our lives and the universe. Through sight, it allows us to perceive and communicate with the world around us. Our eyes are sensitive to the visible spectrum, enabling us to see colors, shapes, and movements. Sunlight warms the Earth and drives weather patterns. It is also essential for photosynthesis, the process by which plants produce food and oxygen. Astronomers study the universe by analyzing electromagnetic radiation. Telescopes capture light from distant stars and galaxies, helping us understand the cosmos's vastness and complexity. Does light have mass? Light composed of photons is both fascinating and elusive. Let's explore its mass-related intricacies. First, let's talk about photon mass. Photons, the building blocks of light, are massless particles. According to theory, photons possess energy and momentum, but no rest mass. Experimental evidence confirms this within strict limits. But light isn't just about particles. It also exhibits wave-particle duality. Light behaves both as a particle and a wave. Early theories, like Newton's corpuscular theory, considered light as tiny particles, but experiments revealed its wave-like nature. Later, Albert Einstein and Max Planck showed that light can behave as discrete particles known as photons. Now here's where it gets even more intriguing: energy and mass. Photons have energy, and Einstein's famous equation, E equals mc squared, relates energy to mass and the speed of light. While photons lack rest mass, they behave as if they have mass due to their energy content. We call this relativistic mass, which is applicable when an object is in motion. Now, let's delve into one of the most fascinating concepts in quantum mechanics, the dual nature of light, also known as wave-particle duality. This phenomenon describes the paradoxical behavior of light as both a wave and a particle, depending on the experimental conditions. First, let's explore the wave behavior of light. Light exhibits wave-like properties such as interference and diffraction. When light passes through narrow slits or around obstacles, it creates interference patterns. Thomas Young's famous double-slit experiment beautifully demonstrated this wave behavior. In this experiment, light passing through two closely spaced slits produces a pattern of bright and dark fringes on a screen, a clear indication of its wave-like nature. But light doesn't stop there. It also exhibits particle behavior. Light can behave as discrete packets of energy called photons. The photoelectric effect studied by Albert Einstein showed that light can eject electrons from a material like particles. Photons carry momentum and energy even though they lack rest mass. This discovery was pivotal in understanding light's dual nature. Interestingly, wave-particle duality isn't exclusive to light. Matter, too, exhibits this duality. Electrons, for instance, can behave both as particles and waves. Louis de Broglie proposed that all matter has both particle and wave characteristics. We can think of particles as bundles of waves or wave packets with effective masses. In our previous scene, we explored the wave-particle duality of light, a cornerstone concept in quantum mechanics. But how does this duality manifest in real-world phenomena? A fascinating interaction between light and matter that revolutionized our understanding of physics. Let's break it down. The photoelectric effect occurs when electromagnetic radiation such as light falls on a material and causes the emission of electrons from that material. These emitted electrons are known as photoelectrons. The photoelectric effect was first studied in the late 19th and early 20th centuries. Classical electromagnetism predicted that continuous light waves would gradually transfer energy to electrons, eventually causing their emission. However, experiments showed a different reality. Electrons were only dislodged when the light exceeded a specific frequency, regardless of its intensity or duration of exposure. Einstein's explanation. In 1905, Albert Einstein provided a groundbreaking explanation. He introduced the concept of photons, discrete packets of light energy. According to Einstein, light isn't just a continuous wave, it's also a swarm of these individual photons. Photoelectrons are emitted when a photon's energy surpasses the material's binding energy. Significance. The photoelectric effect was pivotal in proving the quantization of light, demonstrating that light exists in discrete packets. This discovery played a significant role in developing the concept of wave-particle duality, showing that light and electrons exhibit both wave-like and particle-like behaviors. The photoelectric effect has numerous practical applications. Photodetectors like photodiodes rely on this effect to detect light.